I want to give you some tips about the geometry project. So a large part of your grade is the final geometry project. And what do you need to do? You need to find some subject area where you can include at least 5 proofs. All right, so it would be helpful. What I consider a project is to get them all grouped around a theme, right? And we'd like to understand the historical context, who was interested in solving the problem, what did it lead to, which mathematicians didn't manage to solve it. And I'd also like to focus on how did they prove their results originally, because that might be far different than what we would do now. So you need an area that will allow you to do at least 5 proofs. Now, I'm not going to go over all of the project features, but I will point this out. We're not expecting you to do original proofs, but you shouldn't just recopy somebody else's proof into your paper. You should understand the geometry and then go ahead and put it in GeoGebra and then use some screen grabs to go ahead and get that into your paper. And make sure that you justify the statements in your proof. And since it's class, where possible, we want to reference our theorems and our axioms to justify it. The proofs you get will be justified in various ways. And I want you to tie it into our proofs. Okay, so you're like, wait, project ideas, what am I going to do? All right, well, so I've created, if you look here in the geometry project section, which just got published this morning, you can see there are 4 big pages, right? So the first one is about the nomen. I believe the G is silent, but if you want to pronounce it gnomen, go for it. Uh, and this is the idea um, that it was a lot of their pattern seeking idea. Um, and then the nomen is the part of a figure that you have to add to it to make it similar to the next thing in the pattern. So there's all kinds of cool thing, a lot of number theory stuff that they came up with. First of all, there's triangular numbers, and then of course there's square numbers. They have rectangular or oblong numbers. They have pentagonal numbers. Uh, and then they go to septagons and octagons and nonagons, non-gonal, I don't know, polygonal numbers is what they call them eventually. And so there's a lot of cool number theory and relationships between them. And the beautiful thing is they use these gorgeous proofs, right? They say that so they do these dot drawings. This would be an oblong number, a 2 by 3 rectangle. And their argument that an oblong number is always the sum of 2 triangle numbers is they just draw a line through it right here. So you see the triangular number below and above. So um, I have some really interesting proofs that they do with this number theory, but it's all geometric number theory. And then various various other ideas are also included. So a second topic I put together, a big broad topic, is quadrature. Now, I think we're all familiar with the compass and straight edge constructions that the Greeks did, but why? I mean, why were they doing compass and straight edge? And it was because of their idea of area. And they thought of area as always being square, and they would make these constructions to find a square that had the equivalent area to whatever triangle, parallelogram, or rectangle they were dealing with. Now, they also managed to do some rather interesting quadratures. For example, the estimating pi, calculating pi actually, um, and one of the interesting ones, calculating the area under a parabola. So let's say this is going to be an imperfect parabola, but you have drawn a parabola and you put a line through it. Then Archimedes actually found a way by using successively smaller triangles to be able to calculate this, basically using the idea of limits. So the Greeks really loved quadrature, and they even solved quadratic equations. That'd be a great project, is to learn how to use quadrature to solve quadratic equations, which, by the way, is where the word quadratic comes from. So check out that page. Regular polygons. So let me flip over there, right? So we even have a video showing you how to do the compass and straight edge. constructions of these polygons. And and then finally, if we jump back here, we have Cut the Knot. So Cut the Knot is a great website with all kinds of things. And as an example, it has 122 different proofs of the Pythagorean theorem. And what's cool is the author, whose name I can't pronounce except his first name. He went by Alexander. He went by Alex. Has commented on, where they're beautiful or interesting or important. And then each of these pages has project ideas. Now I did put some project ideas here at the bottom. These are some major areas where you could easily select a theme and do 5. So hyperbolic geometry, projective geometry, duals, and the dual of a geometry. So there's this idea that if points become lines and lines become points, what happens to your geometry? So think about Fano's geometry or one of the finite geometries. What if you had just switched all the words line to point and switch all the words point to line? And it turns out that the dual is also a geometry. It may or may not look the same as the original. So that's interesting stuff. The Euler line, so when we start doing the concurrency theorems, you'll learn that the medians of a triangle, for example, are concurrent at a single point, and the perpendicular bisector of the sides of a triangle are concurrent at a single point. And it turns out that several of these concurrencies are on the Euler line, and there's lots of other things, interesting things that are on the Euler line. So there's all kinds of proofs in there. Tessellations and wallpaper patterns. This is different objects that can cover a flat 2D area, completely cover it. I don't even know how to pronounce this. Icosian calculus, I guess. But this is really cool. This is the very beginning of using group theory to algebraic group theory to talk about groups of geometric classes, right? So this was actually the icosahedron, which is a regular polyhedron, and the different rotations and reflections that could be done, and return it to a place where it's still, I don't know, maybe an easier way to see it is to think about a Rubik's Cube, right? And the different ways that you can turn a Rubik's Cube and it's still a cube facing the same direction as before, right? You don't want to turn it just 10 degrees, right? Because it's not. You have to turn it 90 degrees horizontally or vertically to have it in the same position as before. You might have different sides facing you, but to keep it in the same position. All right, and then I just listed a ton of geometers. There's a big list on Wikipedia that I found that looked good, but I actually took the time to make sure that they did enough actual geometry that you could check. You should be able to do a project on that person. So I also did that for each of the pages, right? So with the nomens, I gave some explanation about what they might be. And then I have a bunch of project ideas that you can take a look at. For quadrature, same thing. And here's a nice video about Archimedes, right, who basically was doing calculus. And the Greeks had this kind of objection to infinity, but they used limits and infinity. And the joke here is that, I could have discovered calculus if I actually, had a modern view of infinity. So then there are different project ideas, and yeah, cranks. So that's definitely something to take a look at. Cranks are absolutely hilarious group of people. Ridiculous group of people. Regular polygons, again, I pointed at this one already. And so this is a pretty wide range of things, and there are lots of interesting constructions that are related to regular polygons or use regular polygons in their development. How to find a certain number, how to construct certain things. Also, pentagrams are an object of, there's just a myriad of interesting things in pentagrams that you can look at. And then the final thing I want to point out is Cut the Knot. And definitely click on this link and check out Cut the Knot. It is a fantastic website, and um, and you can just check the geometry index, for example, is just immense and goes on and on and on and on and on. And I'm not going to spend a bunch of time there, but they do have good graphics. Also, you can search the site like this. I'm trying an advanced Google search where you put this site colon in front of this. And by the way, this is a copy link here that will allow you to just copy this and paste it in. And then you just change this word to quadrilateral or kite or rhombus, and it will bring up all different kinds of articles from cutthenot.org on that topic. And so you might find something of interest that way. Also, I've just gone in and found some from Cut the Knot that are really cool. Um, if you're interested in, Japanese mathematics, this is really cool where they're taking um, pentagons and drawing all the diagonals from a particular vertex, and then they're inscribing circles. And of course, my drawing's going to be awful. But then you've got these inscribed circles of different sizes. Um, and and so yeah, you can certainly search for anything related to Archimedes. He was a great geometer, all kinds of stuff. If you're interested in some of the pre-Greek mathematics, the Egyptians called geometers rope stretchers, right? Anything related to Apollonius, of course. Morley's miracle, which is a rather interesting idea that's more recent, and Siva. So just throwing out ideas that you can find, and I put some links to them where they're on cutthenot.org. So by the time you see this video, there's going to be a D2L project proposal activity that's going to be due. So look at the project proposal. It doesn't have to be a long one, but you have to pick an idea that you're sure will have 5 theorems that you can prove. And that's it. Just definitely don't. Oh wait, before that isn't it. To complete the thought, you do not have to use one of the project ideas from this area of our class notes, online class notes. You may choose a project of your own, but you might want to look at some of the sample ones that I've suggested so you know that you're getting a subject or a theme that has appropriate level and depth, right, that you can get your 5 theorems, right? You need 5 meaningful justified steps in a theorem for it to count, and you need at least 5 proofs that you can do. So you want to make sure that whoever you're studying didn't just do one simple theorem, right? You need to make sure that there's, multiple theorems in that related to that idea that you can do. So have fun, pick something you really like, and enjoy it.